Here is the next example. In this case, in this example, he gave us a three-phase 208 volts. So remember, whenever it's a three-phase system, the given value is always a line voltage. So 208 volts is a line voltage. 60 Hertz Y connected system is supplying power to a Y connected balanced load. So it's a Y connected source as well as Y connected load, where the load impedance of each branch is 8 plus J6 ohm. So he clearly mentioned it's a balanced load, so each branch is going to have the same amount of impedance. And the line impedance of 1 minus J1 ohm. So here in this case we have a line impedance 1 minus J1. Why do we have line impedance? Because as I mentioned, say for example, if you look into our university, our whole university is taking around 10 to 12 megawatt of power average. Okay, so where is that power is coming from? That power is coming from most of it is coming from the nearest power plant, but it could be any other places too. For time being, I'm going to assume it is coming from only one power plant, which is almost 15-20 miles away from our university. So if you look at the 20 miles you need to run a wire. Every wire is going to have some resistance. That resistance equal to rho L by A. Rho is the resistivity. So what kind of material we are using to build that wire? L is length of the wire, A is cross-sectional area of the wire. So for sure that wire is going to have some resistance. And so the conductor is hanging on in the air, and earth is going to act another wire. Okay, so one plate is going to be positively charged, so it's going to act like a plate. Another plate is going to act like a negative plate, so there is a capacitance effect. So that's the reason it has some capacitive reactance. Most of the cases that capacitive reactance is smaller compared to the inductive reactance, because every current carrying conductor will have some inductance effect. So definitely it will have some inductive reactance. In this case, for this example, I chose this number 1 minus J1. Okay, now the question he's asking about, find the line current, load power factor, source power factor, active power, reactive power, apparent power, consumed by the load and supplied by the source. Okay, now so the first thing I can easily find is the load power factor and source power factor. So load power factor 8 plus J6, I converted that into, this is rectangular format, converted that into polar format, which is square root of 8 square plus 6 square at an angle of tan inverse of imaginary over real, 6 over 8. So 10 at an angle of 36.86. So the load power factor is nothing but RL over ZL, or I can say cos of 36.86, same angle. Okay, it will give you power factor. Now the power factor is 0.8. Make sure you must indicate whether it is lagging power factor or leading power factor. Here 8 plus J6 it's an inductive load. Because of the inductive load, it's a lagging power factor. Now, okay, so this is the circuit diagram I draw. Now since it's a balanced load, what I'm going to do, I'm going to here it is grounded, here it is also grounded. What I'm going to do, I'm going to separate this part. Okay, I'm going to represent here. So I have 1 minus J1, 8 plus J6. Okay, now I found the VPH. Since it's a star connection, VL over square root 3, 208 over square root 3, 120.1 is the phase value, phase voltage. Now what is the total impedance here? 8 plus 1, which is 9, plus 6 minus J1 plus J5. So 9 plus J5. So total Z in polar format 10.29 at an angle of 29.05. So source power factor is R over Z, 9 over 10.29, or cos of 29.05. You will end up with 0.874 lagging. That's the lagging power factor. Now I'm going to find the total current supplied by the source, phase current IPH, which is VPH over Z total. End up with 11.67 at an angle of minus 29.05. So the current here is 11.67. Same amount of current passing through the line, same amount of current is passing through the load. So that's what I indicated here, 11.67, 11.67, 11.67. Okay, so in this case line current, phase current are same. So because of the Star connection, line and phase currents are same, so that's what I gave you, or that's what the line current. Now we'll find the source power factor. P source equal to square root 3 VL IL cos theta, or 3 times VPH IPH cos theta. Since I'm doing the source, we have to use the source. Or another formula for this is 3 times I square times R total, because the power always is going to consume in the resistor. Okay, so I think I used this 3 times VPH is 120.1, IPH is 11.67, cos theta S is 0.874. So we found that P source equal to 3675.38 watt. So if you use 3 times I square times R total, so 3 times I square, which is 11.67 square, times 9, it must be the same number. I mean, there is a small error in there. Now Q source is square root 3 times VL IL sin theta source. So theta S, we already know theta S from cos inverse of 0.874, which is 29.07. Sin theta S is sin 29.07, which is 0.485. From this I found Q source. So complex power is 3677.1 plus J. This is plus J because still our total impedance is 9 plus J5, so still it is taking reactive power. Okay, so source is supplying 3677.1 watts of active power, 1785.73 watts of reactive power, so that's total complex power. So if we convert that into apparent power is nothing but square root of P square plus Q square, apparent power of the source. So these two are the source. Now he's also asking about the load, how much the load is consuming. Okay, now when it comes to the load, basically that out of this 3677 watt, some power is going to be wasted here in the line, and some power is going to be delivered to the load. So how much power is going to be delivered to the load? So I can find power losses in the line, active power losses in the line, active power losses equal to 3 times I line square. Why am I using line? Because whatever current passing through this resistance, this 1 ohm resistance, that's what I care for. So here the current passing through this is the line current. So 3 times I line square times 1, that will give me the line losses, which is 3 times line current is 11.67 whole square times that R line is 1 ohm. That value I have 408.56 watt. Okay, that's the power losses in the line. Now reactive power losses in the line, you can use the same formula. Instead of R line, we're going to use the XL. Reactive power losses equal to 3 times IL square times XL. So 3 times 11.67 whole square times 1. This value is also 408.56. This is var, volt ampere reactive. Now power consumed by the load PL equal to, can I say this as P source minus P line losses? Okay, so PS minus P line losses. Now can I use 3 times VPH IPH cos theta L in this case? You can use this formula, but the important point here is it must be voltage across the load. Okay, must be voltage across the load. Now whatever we found, 120.1, that is the voltage across the source. So we found the voltage here, 120.1 volt. Okay, out of this 120.1 volt, there is some voltage drop across this. The remaining is going to go over here, maybe 110 or 105. I don't know the exact number. That's the reason I'm not able to use this formula. Okay, so I know these values. PS is nothing but 3677.1 minus 408.56. that value is 3268.53 watt. So that is the power consumed by the load. So source is supplying around 3677.1. out of that, some power is wasted in the line, the remaining power is reaching to the load. Now we can find the same way. Q load equal to QS minus Q line losses. But here is one important thing you need to remember. Now when it comes to the reactive power losses, basically I would say this is not a loss, I would say this is a gain, because what do you have in the line? In the line we have capacitive reactance. So capacitive reactance always produce the reactive power. It never consumes the reactive power, it produces the reactive power. So basically whatever reactive power losses, this must be negative number, because produced by capacitive reactance, by capacitors. Okay, so when it comes to Q losses, so Q source, whatever that value is, 17.85.73. so 1785.73 minus 408.56. as I mentioned, the line is not losing any Q, basically it is supplying Q, so that's the reason you end up with a positive. So that value 2194.29 volt ampere reactive. I hope you understand this this positive here, because this is supplied by capacitive reactance or capacitors. Capacitors in the line. So S line must be 3268.53 plus J 2194.29. So out of this, 1785 is coming from the source and 408 is coming from the line. So total is 2194. So that's volt ampere. You can say S load, the complex, this is complex, basically complex power. Apparent power equal to square root of PL square plus QL square. So that's P, that's Q. I have 3936.75 volt ampere. That's the apparent power. I'll stop this video here. Next video I will solve more examples. Thank you.